Yeah, so welcome everybody. My name is Stepan Pushkarev. Today I'm going to talk about model monitoring in production. Just a quick intro about myself, why I'm actually talking about this topic. That's 2016. I posted that blog post and KD Nuggets just was trying to socialize, evangelize the fact that we basically, as a community, we need better tooling, more tooling for, in this case, it's just big data, but actually what I meant is machine learning and data science, what we call it right now. And the few takeaways from that blog post was we need tools evolution, better tooling, as I mentioned, education and cross skills, so machine learning engineers will learn Docker, will learn AWS cloud, etc. And improving the process, so like DevOps-like, at that time I was calling it DevOps-like experience for machine learning, so we needed that to streamline the processes, to describe our workflow, machine learning workflow. So it was very high-level blog post and ideas, but then it materialized into a few open-source projects that we started, and we got some traction from that early days in the community, and actually spun off the company that called Hydrosphere, which is the messaging was also very kind of broad of, hey, let's do something good in machine learning space. For like better tooling and other things that I mentioned. Then we were categorized by different analysts and like Gartner-like analysts as a model management company. It's good to be categorized somehow. So now you can introduce yourself and say I'm running a model management company. It's a hot place, still pretty wild. You see many startups, many tools, open source cloud tools. And this talk is basically based on our journey that we went through from the simple tooling to Dockerize the models, provide a nice interface for machine learning engineers and data scientists, to more sophisticated things like, okay, now you're in production, what's next? And the first thing that we face in production is actually the monitoring. Whatever we deploy, at the end of the day, everything is software. So to be monitored, to be alerted, to be debugged and observed in production. So I would use this self-driving car analogy just for the sake of simplicity here. You remember these things from way more. Back to 2010, they reported they reported that when they made those loops in Bay Area in self-driving mode, and that time it was considered as a real win. So we were expecting to have our self-driving cars on our roads pretty soon. And after that, they drove. That screenshot was taken about a year ago. I think right now it's 10 million miles for further testing and in a self-driving mode here. So, and the question is, where is the last mile? So we drive, we explore that inference space. We train our models, simulate the traffic we test our models in a simulation environment and real-world environment, and it never ends. And now it's 2019, and we have this launched on a very small, quite overfitted area. I would say that greater Phoenix area. They basically overfit the models to this specific area. So just they learned every kind of feet of that space, and this is way more. It's Google. It's like the Googles of the world. They're still solving this problems of exploring and uncertain inference space here. for smaller companies like in the enterprises, this is still a huge issue, of course. And just for the let's have some fun, just to understand, like visualize how big our inference space. This is Vietnam, and by like, if you can imagine the self-driving car, how many years do we need? Okay, let's like. Yeah, let's stop it. So you know where I'm going to, yep. So that's kind of you can imagine how many years you need to basically to learn this type of like culture, to this type of environment, to deploy a reliable self-driving car there. So of course I'm using this. It's super like edge case, but this is just to illustrate you like the that journey from the Bay Area loop to exploring different urban areas in different states, in different cities, in different countries, in different cultures. And we did some also simplistic test. We took a Berkeley data set for self-driving cars. The data set that has been taken in Berkeley, trained the image recognition model, one of the ResNet model, as I remember, or MobileNet here, on that data set, and then deploy this model in a different urban area. It looks for us human beings, it looks pretty much the same. But we were like researching how the model will behave there, and if it's possible at all to identify that drift between Berkeley area and another area that may look very the same. So we kind of we used that. So and we happen to have just a slightly different traffic lights there. They have this like green arrow placed in a different different square, and all of the sudden our models that our like canonical architectures like ResNet and others that you know, they're not reliable enough to. And that models and the data sets that we train our models with, they're not reliable enough to detect that like very slight concept drift between two different urban areas. And we were experimenting with different models, like monitoring models, that actually identify this concept drift between Berkeley dataset and a different dataset. So that experiment led us into more general approach, general idea. How can we basically build a system that will help machine learning engineers or machine learning operation team to identify those edge cases as we kind of go live in production, and fill those edge cases back into the training process, so we can close that loop between the first model in production and the next model in production. So, very kind of toy example here as well, just to kind of illustrate that concept drift things. So there is you can imagine there is a classifier that can classify between the orange circles and green squares. So everything else that is beyond this data that model has learned so far is basically uncertainty. We don't know what's there. There might be some gradient edge case in between those clusters of the data we've seen so far. There might be a new concept that we've also never seen there, just a new traffic light here. There might be a concept drift, so the world is being changed over time, so we also should be able to detect this. The title of this slide is not correct, but anyway, so just to formulate the kind of machine learning problem here, if we talk about like image data, we researched that problem in general, but the image data is just easier to illustrate here. And the image data is the most complicated from that, from all the different use cases you can imagine here. So in production for like we used, for instance, like the monkeys with the black faces for training, and then all of a sudden we have these monkeys with the red faces in production. And can we basically just tell data scientist, tell machine learning engineer, hey, there is a new concept here. So a bit theory. So what should we monitor in production for the machine learning models? Of course, system metrics, latency, throughput. It's a software. We should monitor the kind of that boring metrics that I'm calling boring metrics. Model metrics. What's there? Some like first-class citizens are like quality metrics, like accuracy, the confusion matrix, etc. If you have ground truth labels available, so you can like continuously recalculate this the same metric that you used in training process and just plot it over time. So that accuracy is not just one number. That you have accuracy for training, you have accuracy for testing, you have accuracy for different maybe like evaluation data sets, and you have accuracy over time in production. That's easier, but not always kind of possible. Then what else you can do? You can monitor your inference output and do a profiling. For instance, if your model outputs the classes, you can learn that distribution over time and say, hey, like in training, in my validation data set, I have like particular distribution of my classes, and in production it is different. Is it an issue? Maybe yes, maybe not. You just probably need some like insight. Hey, there is something different, and as a data scientist, you can take a look and make a decision out of it. Some other data metrics that you can monitor, you can work with. So per request metrics. So each individual request could be anomalous, for instance, or it could be out of the certain range. There are batch metrics that could be done on a kind of sliding window. So for instance, like KS test. So you can apply a KS test for a particular feature or all of the features and basically compare it with the training distribution. So KS test compares if the two samples are from the same distribution. Kolmogorov-Smirnov test. Statistical test. It compares if two samples of data are from the same distribution. No, not A/B test. It's a statistical test. You can Google a KS test. So the like Kolmogorov-Smirnov test. Yeah. Just so there is a and we call it overall metrics. So you can like look at your training data as a whole and at your production data as a whole and say, hey, this in training data I have a particular distribution of my males and females, and in production I have a different distribution. It might be good, it might be bad, but you should like yeah, more static picture usually talks a lot and provide good insights what's going on in production in general. Why is that? Okay. So what methods we can use to track this on per request metrics? Ideally, it's going to be like unsupervised. So we don't because you can imagine that, for instance, your model have like 100 features as an input, and for every feature you have to like monitor that feature, and every feature would generate like 10 different metrics or 20 different metrics. It's super time consuming to specify some ranges for each feature and some expected values for that feature. So the better way is to do it in unsupervised way, so just to learn these distributions, and then either distributions or other like snapshots of overall training data set, and then use it in production in an unsupervised way. So some clustering, we can use clustering, we can use tree methods, like isolation forest, some PDF estimators. We can use like self-organized maps for this. Actually, yeah, there's also like image and text-specific methods. Basically, the idea is to extract features and apply tabular methods to those features afterwards. And there is also like GANs. I have some slides about GANs. In general, actually, there are many methods you can use to kind of to monitor your data in production. I'll show you a mind map we have. So it's like about 100 different methods there. And autoencoders. I'll talk briefly about autoencoders and GANs now. Why is that? Super fancy animation. So unsupervised batch metrics, it's for instance, for like just tabular data, you can calculate missing values, mean, max, histograms, quantiles, all the statistics you can gather. You basically track it. It's super cheap, and the good thing, you can also, it could be calculated in real time in production. For image, the image profiling is a bit different, but also pretty cheap, and kind of achievable thing is like you can calculate your brightness, colors, briskew, and other like just a high level high level characteristics of your images. So it can give you some insight. For instance, if your camera is like blurred somehow, and it may affect the quality of your predictions, and you just don't know about that, or the hardware thing that started to produce just different images in different resolutions. Sometimes it's the resolution actually increases, and it affects the quality of the predictions in a bad way. For text, also like text-specific profiling, just monitor sentiment, monitor unknown words, monitor part of speech distribution. Also very general picture, but as a machine learning engineer, you don't watch your model every day in production, and if you just look at this once a month, you can just briefly decide if it's good or bad. Like should it be like taken care of or not. Also variational autoencoders and KS tests on raw features. So it's also like batch metrics. I mentioned it before. There is an open topic for multivariative Kolmogorov-Smirnov test. but it's partially kind of covered by autoencoders because autoencoders, if you like if you encode your data, it's basically you can think about this as a kind of statistical snapshot of your data. And of course, all those like metrics and profiling metrics, you can track the changes of like mean of covariance and other like change of missing values. So for instance, like yesterday I had like 100 missing values. Today I have like 1,000 missing values. It's something that to look at. So each statistical metric that we calculate here in the profiling stage is actually a metric to track over time. So what I mean, like and at the end of the day, the single machine learning model, it actually generates like hundreds and hundreds metrics to track.
So you can use the multivariate case test for the whole data set instead of like on feature by on feature?
In general, yes. So feature by feature, the multivariant KS test is super computational heavy. It's kind of there is no currently a solution to how to like do that at scale. So I mentioned it as a like possible solution, but it's not. We've never used that in production. As I mentioned, like many methods, and the challenge is there are generic methods and there are very use case specific metrics, like model specific metrics. Here, a few words about like GANs and concept drift detection for concept drift detection. Basically, the idea is to train your discriminator to learn that blank space and be able to classify not fake between not fake versus not fake, but be able to classify like drift versus good data, good input. So the high-level idea is there, but I'll not go into details. It's just a separate 1 hour presentation. And
I have a question on that though. Do you have anything for detecting at the inference level that somebody's probing? Or probing your model for just detecting the edges. Like, if I send I mean, normally you can see how I'm attacking your model is I'm adding random, take an image and add random noise. That's detectable.
Yeah, it's the same idea. Yes, yes.
So you are detecting the fact that I'm probing your model.
Yes, yes. If you hit that space that we trained our discriminator for, yes, we can detect this and alert and make an alert. Oh, somebody is sending. I'll give you a demo, so it's you can see this. A similar thing, but a bit more interesting. Variational autoencoders. I think I guess you guys all know how autoencoders work. So there's like encoder network. There is intermediate representation, and there is a decoder network. And variational autoencoders, they are just basically apply a slight change on that. They apply some constraint to that latent vector here. So you can learn basically a distribution of your probability distribution of your latent space here. That will help us basically to build, at the end of the day, I'll skip this just for the sake of time saving. At the end of the day, what we want to do, we just want to build this compare probability distributions of two data sets. Whatever method we will use, like variational autoencoders, statistical methods, others, we want to get this type of very simplistic. I'm explaining it in a very simplistic way, but different methods, different like research papers, all of them don't work. Don't try to reproduce them, but actually the promise is just to have these two histograms plotted in on your dashboard and like notifying you hey, take a look at this like long tail and see what's going on there. Let me just switch to some demo. I'm not gonna this is an open source stuff, except some monitoring features. I'm not gonna demo this do a product demo. We also have the deployment part and versioning part, not so sophisticated as mentioned in the previous talk. But what I'm gonna do in this demo now. So I'm trained the MNIST classifier. I'm trained MNIST classifier on a particular data set. You see like some metadata here. Just a canonical model. It is being deployed right now as microservice, and I would like to send kind of simulate a production traffic, basically sending through gRPC images, MNIST data set. Let's look at the profile and monitoring. So it started counting. Let me just, yeah. So this is a per request metric. So it started, it's counting as it goes. Those metrics are more like batch metrics. So they wait for some data to get aggregated. These are, you can see basically debug what's under the hood. So those are requests that we're receiving right now, and some metadata that we capture along the way. I would like to stop this kind of good data generator, and would like to send letters instead of digits to that model. So just to like simulate that concept drift. So we've seen digits so far, and now we send letters. So so this concept drift thing, it started like it became red, and actually I'm just sending a mix of both. Let me just filter just failed requests. You see, it's just letters instead of digits. It's a toy example, but just to give you an idea what may happen in production, so we can imagine everybody has its own use case. It might be just a configuration issue, upstream issue, just an organizational issue. You deploy it, you hand it off the model to somebody, and he started using this model in a wrong way, for instance, or more like self-drive car like use cases. I have
Sorry, what's the y-axis? Like the 100, 800?
Yeah, it's actually 0.8. It should be, it's milli. It's in this case, it's a reconstruction error. For this, under the hood, there is a variational autoencoder in this particular example.
What is the unit you're using for the drift? How are you explaining drift?
So it's a kind of metric specific. Whatever metric you use, this metric can output like any number, and you just set up a threshold there. And
your example, what does that metric mean? The 800 M.
I assume you set the right dash line manually.
That dash line is being learned from the training, of course. But you can set it manually if you want. The output from autoencoders is reconstruction error in this case. Reconstruction error is how well autoencoder can reconstruct the original image. So it just and basically the original image, reconstructed image, and the kind of the error between that. So that's in this case that's the level of driftness, I would say.
And the x-axis is the time?
Yeah.
So, question. Just because I saw on the web app you're showing the samples, how do you guys handle with like data privacy? Because like I'm already seeing the sample here right now, but if it has like
This stuff, it's not a SaaS product. It's usually deployed on your VPC, so we don't.
But I still might have concerns like if I'm an insurance company, maybe I cannot see, like my engineers cannot see these.
Oh, yeah, you mean that way?
Yeah.
Yeah, of course. So if you don't need your machine learning engineers to look at the production data, you shouldn't do that. So the data is we just do not provide this like debug capabilities. It's just a higher level metrics. However, for machine learning engineers, you have to see that data, either anonymized or in a raw format. So it's there is no other way to provide an observability for a machine learning engineer rather than showing a real data to him. So and this is usually for security first customers. We just provide this higher level metrics without the details there.
So I have a different workflow, but I'm not sure how I fit into this. So imagine I have a canary model. I probably have like 5 of them. And they have different levels of confidence. And I have my whiz-bang model, and it has this level of confidence. If they don't know, if they get a different answer and outside the confidence level, then I know one of them is really messed up. And so in that case, the workflow in this is so different than this. This is kind of an analysis of a model in isolation. That's a comparing multiple models, the output saying, do they agree within their confidence? And that happens a lot.
Yeah.
So is that a structure that you support, or is that, because it looks like this is all kind of self-analysis of the model.
We do support with so-called like manual metrics. Basically, you just take you take your confidence and you set up a threshold.
That's the difference that I'm talking about. Yeah. So I have inference running on, say, 2 models at the same time.
Yeah, you can.
And they get a different answer.
Yeah,
They
gotcha.
overlap within their confidence.
That's so you will have on each chart here we have a compare with. So you can run 2 models on different models in parallel and plot those like metrics.
2 is or is it n?
Sorry?
Is it 2 models comparing or n models?
N models here. So that is the same. You compare, and actually it's a good topic, just because it opens a different conversation. What is an A/B testing for machine learning? Like canonical A/B testing, where you split the traffic between version A and version B. In machine learning, you don't split the traffic. You send the same requests to version A and to version B, and then compare an output and filter out. So we call it like response-based A/B testing. So you.
I mean, that's exactly. There's another level past that, which is I have my fast models and my slow models.
Yeah.
In my slow models, I run in production workflow, but they're not going to answer. They're not going to get an answer in time.
Yeah.
Most of the time, they're not going to answer in time.
Yeah.
I really want to know. So now they're no longer coming out the same instant. But I really want to know that they came to a different answer, because my slow model should be more accurate.
Yeah. So we do not have that decision-making like controller, what request to return to the end user. However, we have the capability just to compare them and make some sort of analysis on that.
I just want to know if I can stop building my own.
Yeah. Yeah.
Alongside your inference service?
Yes, exactly.
And then if it
we mirror the traffic, and it's just a separate instance. We do not like interject the actual production traffic. Just few other examples, like what's the text use case, for instance. I'm not going to run this simulation, just to like quickly show you. This one is just a cluster-based monitoring for this text input. The use case is Amazon reviews. We trained the model to get I think the sentiment from the Amazon reviews, and then like as an experiment, we're sending slightly different messages from different websites, also reviews, but the website also was sending like Wikipedia-like data, Wikipedia-like abstracts there, just to fool the model and see how the system is like tolerant and reliable for this type of input, and like a different set of metrics for tokenizer. I think we have here is it's unknown, just unknown words, like how many words in your token, how many unknown tokens you have in your vector here. Simple check, no rocket science here, no autoencoders, but what we found really useful for text use cases, just to identify new words or new tokens in your data set. Also, like once you do here, you can different applications. So the machine learning application or AI application may have more than one model. You know this. There is some like pre-processing model, like the main scoring model, post-processing model. Those just for in Google's of the world, yes, they recommend to do end-to-end neural networks. However, in a real world, we still have a lot of like just separate models chained all together into a pipeline, such a real-time pipeline. For this purpose, we kind of we interject the request ID just like as a best practice from all the microservices world, and also we kind of snapshot all the data, all the requests and responses enriched with our metadata into S3, into Parquet, so to have it available for kind of post-production analytics, so you can build like dashboards, whatever you have.
I'm not sure if that fits within your target, but since you analyze models, one of the things, since you're including latency and requests per second, one of the big problems is sizing the hardware. Well, but to be accurate, sizing down the hardware, because everybody just says, what's the biggest thing I can afford, and runs that. And it's usually a separate monitoring system that goes and figures out that you've over-provisioned by 5x. Or figure out when you need to auto-scale, which is, it's an attribute outside technically. I mean, you're doing model accuracy. I mean, you're a model level solution, but that is a data engineering problem.
Yeah, that's we have to solve. We have to solve it for ourselves. Of course, we're also on Kubernetes. We have to we have to auto scale, downscale, and all that we have is the metrics that you see.
That is outside the scope of Hypersphere, or is it?
We don't sell it as a kind of feature, but it's just I think the natural thing that every like deployment system on top of Kubernetes should handle, just auto scaling, and yeah, those when you deploy the models, you do not specify the hardware parameters. We auto scale it.
That was the first talk, but I'm just trying to figure out where you draw your line in terms of profile. And one thing missing would be like, how much of the hardware resources did you use at peak? That kind of thing.
That's a good insight. We don't do that right now, but that's a good insight. We can we can chat about that.
I have a question.
Yeah.
In terms of, so for this latency feature, is it like a form of distributed tracing from like your input? Let's say you're just like lambda style, right? You're trying to have like input to your channel and your output to your channel. Is that latency trying to tell you between each step from input to the output where is all that time being spent, or is it just input output time difference?
For since we look at the particular model of a particular version and the kind of that microservices instance, basically, it's just a latency between the input and output of this model.
So the difference is like, for example, let's say there's time spent in the actual request processing and there's time spent in the actual like computation. Say it's GPU.
This particular one is on just a gateway level, so
Okay.
just round trip latency.
Got it. Okay, because there seems to work condition tracing. It's like, oh, you solved it. It's awesome. Okay, got that.
Yeah. For the thing I want to mention here, so of course we're not Grafana-like software, and there might be super complicated analysis you would like to do with your model after in production. And what we do, we basically provide a database for you, like S3-based data lake. We continuously, basically in real time, we snapshot all the requests into S3, into Parquet files, enriched with our metadata. And so we can do interesting things. So it looks like a particular model. Here it's a AWS Glue catalog. So there are like columns that represent the actual model itself, like the label, the confidence, the input tokenized input, and all sorts of the metadata that we generate along the way. We also expose it to the S3, so you can build queries like, hey, give me a particular model joined with another model, upstream model, and fill with where the confidence is like greater than a particular value, and where a particular check has failed. And in this case, I'm just querying all the Amazon reviews requests that have more than particular threshold. So they have a lot of missing words in this case. So the missing words means that model have never seen those words before. So we can basically mine and explore that data to make the next iteration in your model, the development here. So the kind of one of the feature I like is kind of openness. We do not log that data. We expose everything that we have into S3 in a very kind of optimized and readable format. So we can hook any like BI tool here. You can hook just do like Jupyter-based like data exploration here. So and in for some of our customers, it becomes your like ground truth data lake at the end of the day, just because it's fresh out of production, and there is no any like intermediate state in between the production and the model training here. Basically that's it. I'm open for questions.
Very innovative product, very impressive. My question is this: so you compare production and your training, compare the data, see data whether has drift or change, such as you mentioned earlier, for text data, what's any new words or sentimental blah blah. My question is, then you also monitor the result, like a confusion matrix. Do you think just all of them is sufficient? Say I only look at the data instead of the inference result.
Result? What do you mean by result?
For example, you have some data, say Amazon review, because you want to check in production whether this review data has changed. Then you also want to change the prediction result and inference result, the output of the model. I just wonder whether one is more important than the other, or both need to be monitored.
Both, of course. So if you have that ground truth data and you can calculate your accuracy, fine, of course. You should calculate it continuously and plot it on a dashboard. If you, but most of the cases that I've seen, you don't have the ground truth data available right away. It's either some like very expensive labeling process, or it's the data for fraud detection, for instance. The fraud will, when you discover it, it's too late. You know, if you discover it at the end of the day by your accounting team, it's already too late. You should have some early signs of this patterns, or just when you model when you're able to calculate your accuracy and your confusion matrix. That means that kind of your model already failed. You know, your model already failed, and okay, no, that's fine. We can.
When you say ground truth data, you mean the model result, output result, the accuracy.
The actual labels. Okay, let's wrap it up. Thanks for the questions. Happy to chat afterwards.